Yesterday, we wanted to calculate some area and volume. Really, we just wanted to calculate volume. But we wanted to think about how we calculated area before. So we're going to use volume is cross-sectional area multiplied by height, because this is just how we calculate volume. Whenever we had length times width times height, that was just the area of one of the faces of a rectangular solid multiplied by the height. When we write the volume of a cylinder as pi r squared times h, that's the area of the circular face of the cylinder multiplied by the height. Because this is calculus class, whenever we encounter something like multiplication, we go in and try to make one of those factors continuously variable, because that's the calculus game. So because this is single variable calculus, we're going to have a variable cross-sectional area. We're only going to be able to vary the size. We won't be able to vary the shape. So the example that we had yesterday was a cone that was cut out of a cylinder. The cross-sectional area was always a circle, but the circles had different sizes. So we had a constant shape, but variable size. This is so that we could write one formula for the volume. We could say pi r squared and just vary the radius of our circle, of our cross-sectional area. So that's the big idea. Same thing that we always think about when we're thinking about the definite integral or integration in general. Integration is multiplication, but one of the factors is continuously variable. Here's our restriction, because we're playing the single variable calculus game. Right. All right. So let's just take this a little bit further. We have a tetrahedron. That's a shape that has four equilateral triangles as sides, otherwise known as a D4, otherwise known as a D&D caltrop. This is the one that you do not want to drop on the floor. All right. So the first thing that we want to notice is that this is just a triangular version of the cone that we had yesterday. So this is just a triangular version of the cone from yesterday. This is just a triangle version of the cone from yesterday. Let's think about where we can get this shape. Let's think about some geometry that's going on here, and then see if we can get some insight. Maybe we could take a guess at what the volume of this tetrahedron is going to be. Take a guess at what the volume of this tetrahedron is going to be, and then all right. I just realized that I drew a nice face here, but I didn't draw a nice floor. So I have to try to draw the floor consistently, and that's always harder. Set some kind of funky angle. I also don't want those directly above each other. Could have done a pyramid. Could have made life easy on myself. Could have done a pyramid, but I didn't. So we're gonna do a similar thing that we did yesterday. Yesterday, we looked at a cone, and we know that a cone is formed by taking a cylinder. A cone is formed by taking a cylinder and just sharpening to a point. Specifically a point above the center, but it doesn't have to be as far as the height goes. So what we're going to do is we're going to imagine cutting a tetrahedron from this triangular prism. So we're going to imagine cutting a triangular prism from our tetrahedron. Now, what we want to notice is that I did not label the height of this particular I'm checking my bag to see if I have one. What we want to notice is at the height of this tetrahedron is not going to be 1. So I actually brought a tetrahedron. 4 sides, all equilateral triangles. So some of you might be familiar with this particular 4-sided dice. So on our tetrahedron, sitting over here, wow, I almost got it right. Pretty good. I actually have a 3D model today. The sides are all length 1, but that does not make the height a length of 1. So we have this angle here, this side here is 1, but that's not necessarily the height of our tetrahedron. So we're going to have to calculate the height of the tetrahedron. The reason that we want to do this is that we want to find the volume of this prism just by taking the cross-sectional area and multiplying by the height. So we would need to calculate the height of our tetrahedron. This side here is at 1, this side here is 1, and this side here is 1. The 3 sides are 1. That means it can't be 1 from the bottom here up to the top, from the floor up to the top. But what we can do is calculate, if we look at this from the top, I don't know why I drew it so small. I guess I was too excited that I got it kind of right when I drew the first one. If we look at our the top view, in both the tetrahedron and the prism, from the top, we just see a triangle. from the top, we just see a triangle. For the tetrahedron, or for the prism, we would just see the top triangle. For the tetrahedron, we would see the point and the three sides going down to the corners. This means it's kind of easy to calculate the volume of our tetrahedron. I just need the area of this triangle, and then I can multiply that by the height. So the volume of the tetrahedron, sorry, the volume of the prism will just be the area of the triangle multiplied by the height of the prism. I want to specify height of the prism rather than just say height, because I'm going to say height in triangle. And then we have the height of the prism. So we distinguish between those two. Now for the area of our triangle, we have 1/2 base times the height. And this we can sort out just by looking at the flat picture here. Our base is going to be 1, and our height is going to be the square root of 3. If we just cut this in half, and we make our hypotenuse 1, since it's an equilateral triangle, our angle here is 60 degrees. And so we have a 1/2 adjacent to the 60 and a square root of 3 over 2 opposite 60. Our base is going to be I wrote 1s everywhere, and I was going to have them be 2s, so I wouldn't have this fraction, but fractions it is. We'll have 1/2 times the base of 1/2 times the height of root 3 over 2, and then this is multiplied by the height of the prism. And so this will be the volume of the prism. In this case, we got to multiply because we're dealing with the volume of the prism. The cross-sectional area is always the same triangle. The cross-sectional area is constant, so I just need to multiply the cross-sectional area by the height. So now we can speculate. Since we're forming the tetrahedron, just by taking, cutting, picking a point on the top of the prism, and cutting away the sides, we can speculate.
we can speculate that the volume of the tetrahedron will be 1/3 the volume of the prism. So 1/3 times the √3/8 times the height of the prism. This is what happened yesterday. When we made a cone out of our cylinder, we had 1/3 the volume of the cylinder in the cone. And we speculated that since we have a 3D object, maybe this 1/3 is the same as the 1/2 we get from a triangle. At this point, you should recognize which question I am not going to be answering today. Because if I was going to tell you what the height of the prism was, I would have just written down height of prism. I wouldn't have written height of prism the whole time. So the next thing you need to do is find the height of the prism and write the volume of the tetrahedron as a definite integral. So your job next is to figure out what is the height of the prism and where does it show up in the definite integral. So this is going to be left unanswered, but I wanted you to see this shape as just a triangle multiplied by a height. The triangle is always an equilateral triangle, but the triangle goes from sides of 1 at the base to sides of 0 at the top when it comes to that point. And I want to know the volume of this thing. Now we can go back to our cone from yesterday. So yesterday we solved this problem. It's a problem to which we already had the answer because the answer is not the point of the problem. Integration is the point of the problem, and we need to understand all the aspects of the process of integration. So yeah, we're going to go back from the previous problem, from yesterday's problem to our development phase, where the volume of the slice is pi r squared times delta H. Here's our side view of a cone, where the red line represents a circular slice of the cone. Because going all the way up and down the cone, that slice will always be a circle. So we can write its area as pi r squared. Now, because the size of the circle is continuously variable, we're going to say, let's make the size of the circle constant for some small change in height. Because if we keep the small change in height small enough, it won't change all that much. So that gives us the volume of the slice of pi r squared times delta H. This requires that we define delta H. Yesterday, I said H, sorry, not delta H, define H. Yesterday, we defined H to be the distance from the tip of the cone up to the slice. Whenever you're defining your delta variable, one end is 0, the other end is the slice, and the slice is in the positive direction. So we're going to choose a different H this time. So defining the delta variable. That's what we're thinking about today. So remember, when defining the delta variable, one end is 0, the other end is the slice, and the slice will be in the positive direction. Yesterday, we put 0 at the tip of the cone. We got nice similar triangles, and everything was pretty cool. Worked out pretty easy. Today, we want to do it differently. We're going to put H somewhere else because we have an uncountable infinity of places we could put H. In this case, there's only 2 that make sense. I want to define H to be the distance from the top of the cone down to the slice. I want to put H here. I want H to be the distance from the top of the cone down to the slice, rather than from the bottom of the cone up to the slice. Once we define a variable, we have stated 2 things. We've identified where 0 is, and we've identified the positive direction. This means that H is equal to 0 up at the top of the cone. And down at the bottom of the cone, H is equal to capital H. And down is the positive direction. I don't think I like it in purple. Now we still have to write R as a function of H, but H is not part of a similar triangle. H is not part of the similar triangle. The similar triangle down here is at the tip of the cone. So I don't get to write a similar triangle with R over H, but we're still going to use similar triangles. I'm going to take the radius, the capital R over capital H is going to be the radius, but it's got to be over the height of the smaller triangle, which is here. The height of the smaller triangle will be capital H minus little h. I knew that this was going to happen yesterday. I was going to have an h minus h, and one of them was going to be a capital. I said I should change this to a number, and I didn't. So today I get to regret that choice. This all happened because yesterday I said some small change in height. I wrote delta 8. I said, dude, you should call that delta x. You always call that delta x. You only called it little h because you just said the word height. And then I was like, oh, it'll be fine. This is where I hire Morgan Freeman today. It wasn't fine. He doesn't return my calls. Now, we're doing similar triangles, which means we're just making a linear function. Look how our linear function works. If I multiply r over h times h, I get r, and I have my slope of negative r over h times little h. Because when h is 0, the radius starts at r, and and the radius decreases to 0 when h increases to h. We start at r and decrease by r every h units. But now we have an expression for the volume of the slice, It's going to be pi times the radius squared times the delta variable. Here's the volume of the slice. We want to translate this into a definite integral that will represent with the total volume. And we just need to evaluate the integral at all the values of h. The values of little h that are in play are from 0 to h. So here is where we are multiplying by the height of our cone. We would probably clean this up a little bit before we start integrating. I'd factor out the pi. I would leave this being squared. I just traded my h for x. Sheesh. This is why I shouldn't have 8 o'clock in the morning classes. Normally, we like to multiply things out if we can multiply them out, but we want to compare this to the integral that we had yesterday. The integral we had yesterday was just integrating an x squared or the h squared, so we got 1/3 h cubed, and we plugged in the endpoints. So here, I want to make a substitution. because I always want to take an opportunity to remind you about how substitution works. So I'm going to make a substitution because I really want this thing is being cubed, and there's going to be some constants. So I have a pi. dw is, we're going to have a minus h over r. So the point that I want to make here is that the integral from 0 to h, the integral from 0 to h that we're looking at, this is an x integral. This is where x equals 0 to x equals h. So I can't just write the integral from 0 to h because those are x's and all the x's need to be replaced. If x is equal to 0, that means that w is going to be equal to r. And if x is equal to h, that means w will be equal to 0. So instead of integrating from 0 to h, we're going to integrate from r to 0. When we're doing a substitution, all the x's have to be replaced by w's, and this is how that shows up in a deficit. We don't integrate from 0 to 8 anymore because those are x's. We have to trade those x's in for w's so that we can integrate. And now we're going to integrate from r to 0. We usually don't like integrating from r to 0 if we think of that as being in the wrong direction. If you don't like it being in the wrong direction, or if you view that as the wrong direction, just trade the order of your integration, but change the sign. Instead of, if you don't like capital F at A minus capital F at B, just do -1 times capital F at B minus capital F at A. There's the 1/3 that we were expecting. And there's the volume that we were expecting. I got rid of this negative by changing the order of integration. Instead of going from r to 0, the integral from r to 0 is -1 times the integral from 0 to r. This is not a critical maneuver. as you can see, instead of saying r cubed minus 0 cubed, we would have said 0 cubed minus r cubed, and it would be multiplied by -1, it would have canceled out. But when you're reading math books, and there's integration in the math books, this kind of thing happens all the time. Somehow the author doesn't like from r to 0, so they change it from 0 to r, and then they drop the sign, and they don't tell you what they did. So I'm just telling you what they did. The other thing that we want to take away from this is that we took a cone cut from a cylinder. The volume of the cylinder was pi r squared times h. When we cut a cone out of the volume of our cylinder, we get 1/3 pi r squared h. Another problem that you'll want to look at, in addition to your tetrahedron problem, if we take this volume of a rectangular solid, we know is length times width times height. If from the rectangular solid, I cut out a prism by picking a point on the top and just cutting down to all the sides, we end up with 1/3 of the length times the width times the height. This is a thing that's happened before. If you take a rectangle and pick a point on the top of the rectangle and just draw lines to the bottom of the rectangle, that volume is 1/2 the base times the height. Or that volume, not the volume, the area. Flip that over. All right, those are the things you want to do. Find the volume of this pyramid cut from this rectangle, and also find the height of the tetrahedron that we had in the previous problem. That's going to do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.